Okay, so there's two videos tonight, and in this first one, I'm going to go over the facts you need to know for the test. In the second video, I work a really important example problem that I've actually worked before, but it's so important I want you to see it again. First off, one-dimensional kinematics, which is when we were just moving with things going in one direction. Here are some important things you need to know after this segment of the video. Position, distance, and displacement, average speed and velocity, instantaneous velocity, acceleration, motion with constant acceleration, applications of the equations of motion, and freely falling objects. So those are the key points for this first half of the video. First of all, distance. You might remember the problems with your friend's house in the grocery store. Distance is the total length of travel. So if you drive your car from your house to the grocery store and back, you've covered a total distance of 8.6 miles, so 4.3 miles both ways. Distance is total length of travel. Displacement is change in position. So if you drive from your house to the grocery store and then from the grocery store to your friend's house, your change in position from where you started to where you finished is 2.1 miles, while your distance is 10.7 miles, total length traveled. The displacement is just how far you are in one direction from start to finish. Next, average speed is defined as distance traveled divided by total time the trip took. Most of you are familiar with speed equals distance over time. That's average speed. Don't confuse it with instantaneous velocity or velocity like we might solve for in the kinematic equations. Average speed is just distance over elapsed time. S equals d over t. So think about this question. Is the average speed... Actually, you know what? I don't know why I put that on there. Let's just get rid of that. There is no red car on this slide. You need to know the definition of average speed, total distance over total time. So if I went 10 meters forward and 5 meters back, and that whole thing took me 3 seconds, speed is total distance 15 meters over time 3 seconds, 5 meters per second. Okay, average speed. Average velocity is displacement divided by elapsed time. So whatever our total displacement is, not just distance, but displacement, how far you are in one direction from a starting place, divided by how long it took. And if you come back to your starting point, so if the runner goes all the way here and all the way back, if he comes back to his starting point, his displacement's 0, and therefore his velocity is 0. But let's do this one. Let's say the runner goes 50 meters to the right, and then he walks back 10 meters, and that took him 4 seconds. Well, his velocity is 40 meters, his displacement, over, what did I say that took? 4 seconds, all of it, 4 seconds, which is 10 meters per second. And his average velocity was to the right, because his displacement from start to finish, switch colors, his displacement was still to the right, which was positive. Going fast, because this is just quick review. So to find something's average acceleration, you just do the change in velocity over change in time, or VF minus VI over TF minus TI. And TF is just final time, TI is initial time. Over to the right is a table of typical accelerations, typical average accelerations. You don't need to know any of those, they're just kind of for fun. The only one you need to know is average acceleration of gravity on Earth, which you should already know. So if you know something's change in velocity, you know how long that time took, or sorry, you know how long that change took, you can find its average acceleration, delta V over delta T. All right, Instantaneous acceleration and instantaneous velocity. Remember I told you that instantaneous acceleration and instantaneous velocity are both finding the slope of a certain part of a graph. And that's what this diagram is about. So if I wanted to find the average acceleration from t1 to t2, we would try to find the approximate slope of that segment. If we wanted to find the average acceleration from t2 to t3, we'd find the approximate slope of that segment. And remember, slope is rise over run, or delta y delta x on the graph. Alright, and that's how you find instantaneous acceleration. Remember I told you both last week and in a video, instantaneous acceleration and instantaneous velocity from a graph are just finding slope. So if I had a position time graph, slope is velocity. If I have a velocity time graph, slope is acceleration. Okay, hopefully you remember that. Quick run through. Here's an equation for velocity as a function of time, which I showed you over the weekend how you can get that equation from a velocity time graph such as this one. You've used this equation a bunch, and so I expect you know it. You should definitely know it for the test. And that's it, just showing it to you to remind you about it. Whenever you have an object that accelerates, its position time graph is always a curve. So motion with non-zero acceleration on position time, it always is a curve. Accelerated motion on a position time graph always, always, always is a curve. And that's what the statement at the top means. The relationship between position and time follows a characteristic curve. So it's a curve that pretty much always looks like this when you have positive acceleration. If the thing had negative acceleration and we're slowing down, remember we did that one day, it kind of looks like that because it flattens out at the top because it's slowing down, may even reach zero velocity, in which case the position stays constant. So remember, slowing down curves like the orange one, speeding up curves like the red one. And of course, remember to always read your axes. That was a big problem on the 2 quizzes ago. Next, if something starts falling from rest, so if I had my hand up here holding this ball and released it, every second its velocity increases by 9.81 meters per second. So after the first second, its velocity is 9.81 meters per second. After the second, 19.6 meters per second. After the third, 29.4 meters per second. After the fourth, 39.2 meters per second, which are all multiples of 9.81 meters per second squared. So our acceleration on Earth from gravity is 9.81 meters per second squared. And here are some velocities after a certain time. The point is that every second, the object gets 9.81 meters per second faster. Also, over here are some distances. You can get all of these by doing 1/2 gt squared. If all you have acting on something, or all you have on an object is its acceleration, no initial velocity, no initial position, then its position is determined by the equation 1/2 gt squared. If it started from rest at position 0 and just fell. This graph, because where this problem comes from, we were still just talking about motion in one dimension, but as we know, this should really be y pointing up and down. Anyway, showing you what an object does if you just drop it straight down. Alright, any projectile follows a parabolic path like so, where velocity points along, and as you know, the upward velocity gets smaller. Not the x component, the x component would stay constant, but the y component gets smaller and smaller and smaller until there's no y component at the top, and then the y component of velocity gets bigger bigger, 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 until the y component is exactly what you started with, except negative. So think about it at first. When you throw something up, it starts out with an upward velocity, ends with a downward velocity. It turns out that the y component of velocity is the same in both places, just negative of each other. You should also know that all along this path, gravity is always pulling the object straight down. So gravity is always pulling straight down. So the object's acceleration vector stays the same size. It's always 9.81 meters per second squared. And I'm drawing acceleration in blue, trying to keep them the same size, but always pointing straight down because Earth's gravity pulls straight down. That's all. All right, some important things you should have gotten out of the first half of this video. Distance is total length of travel. Displacement is change in position. Average speed is distance over time. Average velocity is displacement over time. Instantaneous velocity is average velocity measured over a very small time, which just means finding the slope of one small section of a graph. So you could even rewrite this last note. Instantaneous velocity is finding slope of one section on a graph. And just so we know what kind of graph, instantaneous velocity comes from a position-time graph, slope of a position-time graph. Other important things you should know from the first half of this video: instantaneous acceleration is just like instantaneous velocity, but now you're dealing with a velocity-time graph. And even though it says measured over an infinitesimally small time, that just means one tiny section of a velocity-time graph. Average acceleration is change in velocity divided by change in time. People typically use the word deceleration to mean decreasing velocity, and that's where your velocity is going one way and your acceleration is pointing the opposite way. So whenever you have deceleration, your acceleration points opposite your velocity, and you usually would just call that negative acceleration. Constant acceleration, we have three equations of motion that relate position, velocity, acceleration, and time. Those three equations, please say them with me, are v equals v naught plus at, x equals x naught plus v naught t plus 1/2 at squared, and v squared equals v naught squared plus 2a delta x. And all freely falling objects on Earth have a constant acceleration of g equals 9.81 meters per second squared, pointing straight downward, always on Earth. Okay, moving on to the next half of the video. Quick review of vectors. A scalar is a number with appropriate units but no direction. A vector is a quantity that has magnitude and direction. So whenever you give a vector, whatever you give has to have magnitude and direction, number with units and direction. Vector components, if you know A, then the x component of A is A cosine theta. If you know B, which is just a vector, the y component of B is B sine theta. Just like if you know velocity, the x component of velocity is V cosine theta, and the y component of velocity is V sine theta, where theta is the angle the vector makes with the ground, or with the x-axis. To find the magnitude, and the computer messed up the scripts here, so let me rewrite this one. To find the magnitude of a vector, it is a equals the square root ax squared plus I don't know why I drew a triangle, ay squared. Pythagorean theorem, c squared equals a squared plus b squared. And the direction on a vector is always the y component over the x component, the inverse tangent of those. Theta is inverse tangent y over x. And that usually is your direction for a vector, just the angle it makes with the x-axis. Also, you can add vectors graphically, not just with numbers, by placing the tail of the second vector at the head of the first. And then you go, when you draw your resultant vector, let me do one of these real fast. So if we have a blue vector and a red vector, whenever I draw my resultant vector, it goes from the tail of the first to the tip of the last. So the orange is my resultant vector. And that's what sum points from tail of first to head of last means. Your sum, or your resultant vector, points from the tail of the first to the head of the last. Alright, now let's turn to the basics of projectile motion. Remember that acceleration is independent of the direction of velocity. So whether on Earth I drop a ball or throw a ball at some angle, its acceleration always points straight down and is always 9.81 meters per second squared straight down. Acceleration in y on Earth is always that value unless you have something pushing or pulling, but we're not there yet. We're just doing projectile motion where acceleration on Earth is always 9.81 meters per second squared downward in the y direction. And x acceleration for projectile objects is always 0. So x acceleration, 0, y acceleration, gravity, 9.81 meters per second squared, downward and usually negative. So we can rewrite our equations of motion, splitting them, or not necessarily splitting them, but having y versions and x versions. And what's happened in these equations is we've taken out the parts we know to be 0. So here there's no acceleration in x, and so there used to be a plus 1/2 at squared, but since a is 0 in x, that part of the equation goes away. Similar things happen in the others. So this is just writing the 3 equations of motion, which I will quickly write above each set. So these first 2 equations come from x equals x naught plus v naught t plus 1/2 at squared. Try to figure out how they got the 2 below it. These over here come from v equals v naught plus at. Try to figure out how they got the ones below it. And then finally these come from v squared equals v naught squared plus 2a delta x. Stop and try to figure out where the equations below that come from. If you have trouble figuring out any of the typed equations, be sure to call me or someone else or ask lots of questions tomorrow. Might need to pause the video if you want to take a minute and make sure you know how to arrive at all the equations on this screen. Alright, maximum range for projectile is when you set its angle with the horizontal, or with the x-axis, at 45 degrees. And what this slide does is just shows you what happens at some other angles. And remember, we kind of intuitively did this by saying the maximum kind of shared part of the angles are when you have tangent of 1 or when y and x are the same thing, when the ratio equals 1. And when you have tangent, inverse tangent of 1, you get 45 degrees. So maximum range for a projectile happens at 45 degrees. I also talked about taking a water hose, having it squirt, and that point where it's no longer moving away from you when you kind of tilt it back, that point is 45 degrees. And so 45 degrees gives you your maximum range because it splits evenly between time in the air, or sorry, velocity up and velocity over. And intuitively, I think about it as time in the air versus time traveling horizontally. So it splits evenly among the horizontal and vertical if your angle is 45 degrees with the x-axis. Some neat things about projectile motion. The size of your velocity vector on one side of the parabola is exactly the same size on the other side. It's just that their vertical or y components has flipped. And velocity in y at the top is 0, but you still have your initial x velocity happening. So all that happens is from one side to the other, kind of exactly on the other side, if you think of mirroring across the middle, the velocity vectors are the same size, just in opposite directions. And remember, acceleration always points straight down toward the Earth and is always the same value. Acceleration g 9.81 meters per second squared, and it always points straight down toward the Earth. I said that twice in this video now, which might mean it's important on the test, just to think about that acceleration always points straight down and is 9.81 meters per second squared. And we are at the end. I know that was fast because it's just review, just tipping you off to things you might need to know. Summary of the last half of the video. Components of motion in x and y directions can and should be treated independently. You got to think of x and y separately. It scared me over the weekend when we were doing the lab that people were putting 9.81 in the x equations because 9.81 belongs with y, never in x. So just remember that x and y should be treated separately. In projectile motion, acceleration is negative g, or negative 9.81 meters per second squared. And in projectile motion, where you set the ground at 0, it usually is most convenient to have gravity be negative or pointing down. And so whenever you do projectile motion, just go ahead and have gravity be negative, negative 9.81 meters per second squared. If the launch angle is 0, which is what you got to play around with in the lab this weekend, if the launch angle is 0, initial velocity has only an x component. V naught x equals something, and V naught y equals 0 for a 0 launch angle, if the launch angle is 0. If the launch angle is not 0, if it's something else, you have to split velocity into its component vectors. So in this case, where it's 45 degrees, Vx is V cosine 45 degrees. Vy would be V sine 45 degrees, where V is the velocity in the direction of this vector. So if you have a 0 launch angle, velocity in x is whatever it started with. Velocity in y, initial, is 0. It's for a 0 launch angle. If you have an angle, you have to split the initial velocity up into its components. This would be V naught. V naught y is V naught sine 45, because I had a 45 degree angle in this example. V naught x is V naught cosine 45, because I had a 45 degree angle in this example. The projectile, or the path followed by a projectile, is always a parabola, always does something like that. And range is the horizontal distance the projectile traveled. So when you figured out where the steel ball would hit on Monday during the lab, you were figuring out the range of the projectile, and the projectile was the steel ball. All right, that was lightning fast because we had a lot to cover. I do work one really important example problem. It's the football problem I gave you about a week ago, and that I worked on the video. So I just copied that part of a video from last week over because I think that's a super important example that you need to see again. I wouldn't think that unless it's like something on the test, so be sure to pay attention to the example in the second video. Good luck studying, and that's all for tonight, except the second video. Be sure to watch it.